we define from chapter 1, from chapter 1 to chapter 3, we did one thing. We defined a state, set of properties defines state, a system at certain moment, equilibrium state, does not change with time. Balance in temperature, this is called a state. Set of properties, for example, mass, volume, number of moles, energy, internal energy, kinetic energy, potential energy, enthalpy. We define enthalpy, which is H was U plus PV, the total internal enthalpy, internal energy plus flow work, PV, energy, everything in joule. So this is, maybe make it bigger, U. And we call these properties extensive properties because they are dependent on the size, all of them. But if you transform them to be independent, like a specific volume, this is number of mole over mass, which is 1 over molecular weight. Sometimes 1 over m, 1 over mw. So you can say nu, 1 over molecular weight, internal energy U small, specific internal energy, K E small, specific kinetic energy, P E small, is specific potential energy, H small, specific enthalpy. So V 1 over m, U, K E, P E, H. These are properties of a state. All of them are intensive properties. And P, T. You can say nu or rho. 1 over rho is nu. And finally, we define something so important. It's called X, quality. Quality is the mass, the amount of mass of vapor over total mass in saturated mixture. So these are all the properties that we discuss in the last few lectures. And if you have any two of these independent, like V and P, H and X, and U and rho, any two independent intensive properties, you are fine. You can get the rest of the properties. You can get everything else. Everything. Like if I get P and T, I can get nu. For example, we said equation of state, P V equal RT. This is the equation of state we gave in the beginning of chapter 3, PV equal RT. Knowing the pressure, for example, and volume, specific volume, you can get the temperature. So this guy simply is R universal over molecular weight. Or directly from table A1. If you go to table A1, you can find all the fluid, all gases. This is ideal gas law. From PV, you can get T. From VT, you can get P, and so on. From any two independent intensive properties, you can get the third. And T in absolute temperature. Always Kelvin if it's SI units. Always Rankine if it's British units. And we define, so every state, this is the properties. State means 1 point. And we said we have 3 ways to get the properties. We have 3 ways to get the properties. For example, this equation, PVT. PVT has 3 ways. PVT has 3 ways. They are very important, all of them. It has, this is a very famous formulation, PVT, pressure, specific volume, temperature. Or you can say P rho T if you want, pressure, density, temperature. There are 3 ways, and you will be asked about the 3 in the exam. And this homework, for example, these ways are equation, ideal gas law. Just PV equal RT. Or PV over RT equal 1. These are the same. This is the first equation. The second one is called compressibility. Can you see this, guys? It was not clear. I use other color. So PV, oops, PV equal RT, ideal gas law or equation of state. The second one is compressibility correction. Compressibility correction. Nelson chart or factor. It says how bad you are compared to the ideal gas law. So something is called Z equal PV over RT. So this Z, we get it from a chart. We have a chart for every fluid, the Z. So we have a chart for ideal gas law. We have a chart, I think A18, Nelson chart. It says, if you give me, for example, P over P critical, T over T critical, I give you the volume. I can get Z, then you can get the volume. If this Z became 1, you will become here. If you are far from 1, you are far from ideal gas law. So if I give you, for example, P and let's say V, specific volume, this P divide by B critical and you call it B reduced. This divide by V critical and call it V reduced. From B reduced, from P reduced or R small and V reduced, you can go to Nelson chart and get Z. Get Z chart. It has pressure down, reduced, R small, R capital. It has temperatures. It has volumes. So with 2 information, you can get Z. From Z, you can get the third with more accuracy, much better accuracy for like correction for ideal gas law. It's a corrector or correction. Last thing is, so can somebody tell me what is the last way to get the relation between P, VT or P or OT? What is the last way? P, VT. What is the last way, guys? Can somebody tell me? It is what? It is what? Steam table. It is what? Steam table. If you have 2 information, go to the steam table. Maybe, for example, table A4 for temperature input for saturated mixture, A5 pressure input, saturated mixture, A6 superheated vapor, which is what we want. Usually superheated vapor, like A6, you have PVT for super heated vapor. Guys, this is for water. Remember, this is for water. If you're talking about another fluid, go the corresponding superheated vapor table. For example, air. For example, R134A, refrigerators fluid. So you need to go the corresponding superheated vapor table with any 2. Let's say you have P and V, you can get T. You have T and V, you can get P. You have any 2, you can get the third. This is state postulate. It says if you have 2 independent intensive properties, any 2, you can get the rest. For example, here, PVT, you can get the third. So easily. Ideal gas law, compressibility correction. So in the lecture, in the end of last lecture, lecture 4, we have an example. I give you, for example, in this lecture, open please the lecture. In the very end, you will see an example. It says, example 384. Example 384. We give you the P, the pressure, was 3.5 megapascal, 35 atmosphere, almost. Temperature, 450 Celsius. Yes. When you use the table, yes. But when you use equation, use Kelvin. Whenever you use this, use Kelvin, please. So 4, you mean add 273.15 to convert from Celsius to Kelvin. Absolute temperature. We need here absolute temperatures, please. So he said, give me the specific volume using ideal gas law, compressibility correction, steam table. This steam table is the exact. Yes, this is exactly correct. There is no assumption. It can be fluid, can be liquid, can be gas, can be. This is exact solution. for gas, liquid, anything, mixture. This is exactly correct, perfectly correct. Of course, you do interpolation or something like that, but still the data is exact, the measurements. So we talk about gas here. We care about gas. For now, we're going to talk about superheated region. The very right region in the chart. We have three regions. Compressed liquid in the left, mixture in the middle between the substituted lines, and a very right superheated region or vapor. So we're talking about the very right. It can be calculated from here or here or get it from the table there. This is actually the data in all your life. You have equation, any equation, Ohm's law, Navier-Stokes equation, any definition of any law, First law of thermodynamics. You can have any law here, Euler equation. You can go here. This is also equation, but with some correction. You need to go chart, get something, then go to the equation. So it's still somehow in between. Finally, data in a table. You have data structure, you have data set, information, all information there, so you can get anything you want. So this guy here you have in this problem 384, the input's pressure, temperature. With these two, convert them to absolute. This is 35 times 10 to the 6. This is 45 plus 273, and you get the correct R, which is for water, it was 461.8. This is, you want R. If you have R universal over molecular weight or table A1. Could you please A1, anyone open table A1 and get me R for water, H2O. What is R for water, guys? Joule per kilogram mole, Kelvin. Can anyone tell me what R is for water? The gas constant for water. I mean water vapor. Can anyone open table A1, please? And go to the row of water and get the R. Table A1.
.4615.
So this is kilojoule. In joule, it's 461.8 joule per kilogram Kelvin. 461, or it's 8314, which is universal constant, divided by 18 molecular weight. It gives you the same answer. Okay, guys? So you have several ways to get this. So plug everything here. You have P, you have R, you have T, you can get this, which is here, was for this problem. It is 0.0954. For this problem, it's 0.0954. Make sense? And what's the unit? Meter cube per kilogram. The second one, you need to go from table, again, A1, get the B critical and T critical, V critical, or here you need T critical, for example. T over T critical. Please go to table A1, give me P critical and T critical for water. What are these values? Everyone need to have calculator and table, please. Help me, because in the exam, I'll give you a few minutes to do that. So you need to do it now, as fast as you can, as more repetition as you can. Repeat it a lot over and over to make sure that you got all the mistakes now. Please avoid to do these mistakes in the exam. And of course, if I found copied, like for example, the same mistakes repeated between two students, it means they are copied. They got 0, both of them. So please do not copy. Don't think the professor is not smart. We are so smart. We can find who cheated from who very simply by just comparing the results and scan them together. So do not think you're gonna get from anyone anything. Because if you did a mistake and you the same mistakes, it means you are cheating. It means you're gonna get 0. Okay. So from table A1, if you get P critical, what is this, guys? So 22.06 megapascal. How about T critical? 647.1 Kelvin. This is the critical temperature and pressure and temperature and pressure for water, for steam. This is the very top point in the chart. I will ask you to draw the chart, for example. So divide P over B critical, we call it P reduced. So you have pressure, 3.5 megapascal, divide by 22, it's 0.158, about 0.16. This is called P reduced. So P reduced, it's 0.16. P over P critical. Now, T reduced is what? T over T critical. Please convert this to Kelvin. Do not divide this by this. If you do not divide, if you do not convert it, you'll get a very different number. So this first, add 273.15 to become in Kelvin, which is 723.15. Divide by 647, so you'll get the T reduced is 1.118. It's a ratio. It does not have any dimensions. Please go to table A18, which is actually A15. I'm sorry. A15. It's Nelson chart. A15 for water. Open it. Go with P reduced 0.16, the horizontal axis, and T reduced, which is a slant lines do like this, and you get the Z value, the compressibility factor or correction factor. Guys, can you please go to table A15, everyone, with the horizontal axis P reduced 0.16? You will see two charts in A15. Can you open table A15? You want to share it with you? Hey guys, do you want to share it with you?
Yeah, that would be great.
Okay, if you go please to our lectures, you will see there is a steam table. So I will share it now. 1 minute. Share screen here. So as you can see here, table A18 is here. Ideal gas property A15. Nelson chart. Nelson Oppert chart. Compressibility or regionalized compressibility chart. Page 921. Go down. Table A15. 1 minute. So this is A11, 12, 13, 14, 15. Can you see it, guys?
Yeah.
So we have here two charts. One from 0 to 1. From 0 to 1, which is a top figure. 1 minute. Move very fast. From 0 to 1, can you see here? The first top figure, be reduced from 0 to 1. The bottom one from 1 to 7. We are caring about the first top. So go down the first top figure with B reduced 0.1, almost 6 here. Can you see this? Here between 0.1 and 0.2, almost 0.16. Go vertically until the pressure temperature line 1.1. This is T reduced. Can you see it? T reduced 1. Can you see T reduced 1, guys?
Yeah.
1.05. Can you see it? Can you see the highlight?
Yes.
Yep.
1.1. Between 1.1 and 1.15. Yes, it's closer to 1.1. It's almost 20% away from this guy. From 1.10. It's our temperature critical reduced value is 1.118, almost in between 1.12. So if you go to with this temperature and this pressure here, you'll find your value somewhere here. It's around 0.98 here. This value, something here, 0.97, 0.965. Try to get it as best as you can with 0.1% error or something, or 0.1 error, 0.1 in terms of 1. So you'll find the Z value was 0.97, approximately 0.97. So what are they here? Z here was 1. Z here is 0.97. Ideal gas law, we have Z is 1. Here is 0.97 using Nelson chart or compressibility correction chart, 0.97. Substitute here, you get a little bit less specific volume. Here multiply by 1, RT over P. Here 0.97 RT over P. And everything in absolute value. Pressure, temperature, and R, of course, the same gas constant. The last one is the easiest, maybe. Last one, which table, guys? Last one, table what? You did already the homework. So last one is what?
A6.
A6. Go table A6 with this pressure, 3.5 megapascal, with this temperature. Actually, the tables are in Celsius. That's good. 450 Celsius, and you get the specific volume. You'll see a close value. So in this case, V, the specific volume was a little bit smaller, 0.0921. Here is 0.0954. Yeah. The last one, if you go to the steam table using the P and T table A6, you'll find the V is 0.09198 meter cube per kilogram. Meter cube per kilogram. Please do not forget the units. 0.09198. Can you see it, guys? In the exam, I'll ask you to solve this problem again. Okay? Maybe with different properties. Let's say I'll give you V and T. So you need to go to the chart and get here pressure, and get here pressure, and get here pressure. So which one the more accurate, guys? Which approach is the more accurate? A or B or C? Which one? Guys, which one is more accurate? Guys, one question. Which one is more accurate? Ideal gas law, compressibility correction, steam table?
Isn't the ideal gas law more accurate?
No, the ideal gas
Steam table?
The steam table is the exact value. Ideal gas law, if it's ideal, you know what ideal means? It means inviscid. There is almost no fluid is inviscid. It means there is no viscosity. It's a frictionless fluid. With like argon, for example, very ideal gas, which is almost doesn't exist in reality. So this is good approximation. It's a very good equation. Like imagine that PV equal RT. General, you know, remember guys, Charles law, Boyle law. You remember this in high school? So this is a very good equation, like fantastic equation, but it's still approximation. It's still approximated equation. It does not represent the reality of gases like vapor. But this is correct. It's forever correct. It's a law. It's correct. But if you have ideal fluid, ideal gas, actually not liquid, gas. Everything here, guys, is gas. Everything here is gas. This guy and this guy mainly gases. This guy can be like gas, liquid, the steam table. We can have liquid mixture. But these guys are only for gases. Please, you are an engineer. You cannot come for a problem with liquid and tell me PV equal RT. Do not do that, please. I don't know what I'm gonna do. Maybe I'll give you 0, not a circle, a square circle. A square 0, I mean. So there is nothing called ideal. There is nothing. No one is ideal. No one is pure. No one is perfect. Correct? So this ideal, does not exist in reality. So ideal gas law, if you have it, yes, correct, perfect. But you don't have it, and you will never have it. So steam table is the most accurate result. So when we get the error, you need to compare this with the others. So we're gonna say this V minus this V over this V. This is called error. So error always by definition is, let's say, the V, absolute V, let's say approximate minus V exact over V exact times 100%. So this is definition of error. So this V minus exact over exact times 100. It give you like 10%. For example, this problem, it has about 3.7% error here. 3% error between this value and exact value. 3% error. It's a very small error. It has 0.13% error here. Imagine this, how small it is. So this one, much better. Error, almost nothing, 0.13%. This is 3.7%. 3.7%. This is 0.13%. Still, both of them are great. Are great, but this one is much better. The compressibility chart. So in exam, I'll give you two properties. I'll tell you, give me the third using ideal gas law, compressibility correction, steam table. You need to use always in the equations absolute temperature. Make sure you can able to use this equation correctly. So I used to use to say something else. There is nothing hard or nothing easy. There is something you know, something you don't know. If you don't know, it's not hard, it's impossible. But if you know, by doing it over and over, so it's easy for you. Okay, guys, got it? Let's move ahead with next lecture. Okay, guys? Okay, guys? Any question? Can you hear me, guys? Hello? Can you hear me, guys?
Yes.
Yeah.
Okay. So I'm gonna do this, okay? So please
Can
make
you go
sure
over
you.
the steps for the compressibility?
Okay, I'm gonna keep it. So
Sorry.
please make sure you repeat everything what I mentioned, everything, do it yourself, your hands. Make sure that. Okay, guys? So today's lecture is different. Today we're gonna move something very interesting, which is chapter 4. We gotta define 4 and a little bit in 2 again. It's 4.1, today chapter 4, 4.1, and 2.2. Then 4.1 and 2.3. These are two merged. This about heat, this about work. We're gonna talk today about work and heat. Something is so important in thermodynamics, heat and work. So again, every state has properties. It has mass. Every state has mass, volume, number of mole, internal energy, kinetic energy, potential energy, enthalpy, has specific volume, molecular weight, or 1 over molecular weight, which is number of mole over mass, or 1 over molecular weight, have specific internal energy, specific kinetic energy, specific potential energy, specific enthalpy, specific pressure, temperature, and quality. Every state has these properties. But let's go to one of my examples. For example, one of the examples was in the last lecture. It was a tank. It has pressure and temperature, and you can get everything like volume, energy, enthalpy, anything you want, entropy. If you have 2, you can't get the rest. Remember this problem? Then I give heat. I give what? Heat. What happened? It became another state, another pressure, and the same specific volume. So you can get the rest. Anything else. So here you have some properties. State, let's say with state 1, and you have here another property which is state 2. Correct? Remember this problem? We did it in the last lecture about how to find the rest of the properties using steam table, or now using equations. If it's gases, chapter 3. So state 1 and 2 can be totally determined if you have 2 independent intensive properties. I think it was here also volume, maybe PV, specific volume. Like I give you the volume of the tank and mass, it's V. And V here is equal V here because it's rigid tank. Anyway, the point here is this. These properties associated with state. These properties associated with state. But this one, not. This is something happening between state 1 to state 2. I add energy. This is called process. I add heat, add work. This is the difference between state property and work and heat. Work and heat are not associated with state. Something happened in a process going from one state to another. Something I did, it changed. Okay, guys, I'm gonna remove this now, please. Okay? Okay? I'm talking about the one that he said, please don't remove it. Okay, I'm gonna remove this now. And you have the lecture. I think the lecture has written. It has all this stuff mentioned. So, what is heat? It's energy transfer. Heat, it's energy transfer, heat energy transfer between 2 states. Energy transfer between 2 states. We call it Q12. So it's a Q12 or Q12, like this. You must have 2 states and heat transfer between these states from heat added, so changing from 1 to 2. That's why there is nothing called Q1 or Q2. It's called Q12. It's called what? Q12. Yes, it causes delta T. Yes, this Q, for example, it creates delta T, which is, for example, T2 minus T1. Yes, T2 is a property of state 2. T1 is a property of state 1. But Q12 is not. They are not properties. Something happened. We have a very special case about heat, which is called adiabatic. Adiabatic. Remember this word forever, guys. Adiabatic. I think we are missing here also. Adiabatic. Q is 0. Like say 2, 3. So the process between 2, 3 was adiabatic. It means the heat transfer from the system across the boundary is 0. Adiabatic. Also, iso, not iso, we call it isolated. It's still adiabatic. There is no heat in or out. So isolated, both. No heat, no work. But adiabatic, Q equals 0. There is no heat. So when you read the exam, as I told you before, you will find the keywords. I said between state 1 and 2, it's adiabatic. No heat transfer from or to the system. Make sense? Okay, if we divide by mass, we call it what? Heat per unit mass. Do not say specific, please. There is no more specific. A specific associated with state, a specific volume, yes, a specific like number of mole, a specific kinetic energy, potential energy, enthalpy, yes. These are properties. Here we say per unit mass. So do not say specific heat. There is nothing called that. There is not. A specific means a property like V, H, U, S, entropy. This called specific properties. We divide by mass. But this heat per unit mass. Heat per unit. So this is called heat per unit mass. Of course, joule per kilogram. If we are talking about SI units. Also, if we divide this Q by T, like Q dot, which is Q over T, it's called power, rate of exchange of heat, or Q dot small. It's a Q over T, which is what? Rate of exchange of heat per unit mass. I'm not gonna say specific, don't worry. So do not ever say this per unit, say this per unit mass. Do not say it's specific. Do not say specific. Say it per unit mass. Yeah, this is heat per unit mass. Rate of exchange of heat per unit mass. Heat per unit mass. Heat rate. This is adiabatic, Q equals 0. So heat per unit mass divided by the mass. It doesn't mean the other one. There are 3 types of heat. 3 types in your life. 3 types. We have seen it from high school. They are conduction, convection, radiation, and radiation. Conduction, for example, if you hold a bar and you heat up from the end. So the heat transfer through this bar by conduction. There is something called thermal conductivity of every material. For example, K of aluminium is 35 watt per kilogram Kelvin. So if you put it like next to the heat, it's gonna transfer up until it touch your hand and you get hot. You can leave it after a while because it's gonna burn your skin. This is called conduction, heat transfer through the solid state. Convection, the heat transfer through fluid. So if you have this bottle, it's very hot, and you put the fan air moving around it. The air is moving above it to cool it down, like a radiator in a car. This is called convection. If you put the water moving around it, also convection. Any fluid moving over body to cool it down or heat it up is called convection. It's heat transfer through fluids. The most famous example, heat exchanger, is a very known typical process or application. Heat exchanger. Heat. These are very typical problem for convection. Heat transfer through fluid, gas or liquid. Fluid general. Finally, the radiation, like what? Can you give me an example of radiation, guys? Can you give me a radiation example in our life?
X-rays.
Exactly. Any ray, any sun, any heat go through space without medium, it calls ray, it's radiation. Heat transfer without medium. It doesn't need medium. Like for example, sun, we have a space, heat comes to us. This is called radiation. This is through medium. This is the same solid state medium. Conduction, the same even liquid, it has also conduction. But when it goes to another state, it's called convection. This is through medium or non-medium. It's called radiation. Heat through radiation. It's rays. Okay, guys, like sun. Sun is a very typical example. Remember, always radiation, sun. Heat exchanger for convection. Conduction, like for example, heating bar in your hand, like solid bar. This is a conduction. There are different notation. For example, we used to say convection, advection. We used to use conduction, like for example, the diffusion. For radiation, we used to say radiation, yeah. But this is, we used to use also diffusion, like diffusion of fluid, advection. Okay, so the more definition you have, the better you are, at least in thermodynamics. Maybe an engineer in generally, but so here, heat, energy transfer between two states, 1 to 2, must be between two states. There is nothing Q1. There is nothing Q1 or Q2. No, but there is Q1, 2. Adiabatic, it means there is no heat transfer. It means Q equals 0. Yes, it causes T1 minus T2 or T2 minus T1, but it doesn't mean there is Q1 or Q2. It means there is Q1, 2, Q2, 3. If it's adiabatic, it's 0. There is heat per unit mass. Per unit mass. Do not ever say that the same word we used in properties. We use here heat per unit mass. Q over, and use small letter as well as what we did before. Q capital for the joule per unit mass. It means Q 1, 2. If it's rate, like power, Q over T. So you can say here the units is watt. Here is joule. Actually, joule is Newton meter. Yeah, it's already correct. Joule per kilogram. So here is watt. Watt is a bad guy. No, it's good. So we have here finally the watt here. Here also watt per kilogram. So Q over M over T. So it's Q over M is joule over second times T. It's watt over kilogram. So this is the SI units. 3 types of heats: conduction, convection, radiation. Sometimes I ask in an exam, give me the 3 types of heat. You're supposed to say conduction, convection, radiation. Simple or not? And I can tell you, I have never seen somebody say it correctly unless like 10% of the. However, you have open book exam, you will see, because you misunderstand the question. So I ask you for types of heat, you give me this. But if I ask you for type of energy, it's different than something else. So this is called types of heat. It's different from type of energy. Energy is something else, energies. So if I ask of heat, give me those. If I ask energy, give me something else, like work, heat. This is called type of energy. This is a different story. This is different type of heat. Heat. Something is hot. How the heat transfer? How it go from one state to another? I mean, how change the state from one to another. So let's take 10 minutes break. We'll come back at 11. Okay, guys? Do you have any questions? I see some down. If you have any question, guys, with me. Do you have any question, guys?
Are you gonna? Will you release like a practice test before the actual midterm, or?
Yeah, I'm gonna post like a review. A review is a summary of all the lectures, very fast review. Then a midterm example. So what I do is like this. I use the last year example, the midterm last year. I give it to you as a practice exam. I can post it earlier if you want. Then during the review, which is few days before the midterm, I'm gonna solve it myself. So you will see everything solved in front of your eyes. Make sense?
Okay, sweet. Yeah. And then the midterm is the 17th.
The what? The midterm is 17th. Yeah, I remember it was 17th. So it's almost 10 days from now. So remember, guys, mark this day. We have almost 10 days or so. So you need to make sure that you know every example in the midterm and the homeworks you solve it by yourself. Do not say I'll solve it later. You're gonna regret. In the exam, you say, I regret. Or even after the exam, because you don't know this is a mistake, because you don't do it yourself. So do the mistake now. Always I keep saying that, do the mistake now. Do not wait till the exam to do the mistake, please. Okay, guys? Let's take a 5-7 minutes break. if you have any. So work is an energy associated with force through distance. We used to say W equal FD. Sometimes we used to say W dot, which is W over T, like power. So again, work is an energy, it's a joule, and its rate joule per second or watt. It's energy associated with force through distance. This is distance. Can you see, guys? Force times distance is Newton times meter. Okay? Again, we can say W small, which is W capital over M, which is what? Work per unit mass, like 1, 2, 1, 2, 1, 2, and so on. It's a work per unit mass. Do not ever say specific here, please. Or W dot small dot, which is work per unit mass per time. Okay? Okay, guys? Okay. Both work and heat, both of them are joule. They are the joule. They have joule units. Please open page 5.2, new lecture. Open page 5.2. 5, lecture 5, number 2. You have it, guys? Page 5.2. Both heat and work are energy unit, which is joule, or joule per kilogram if it's per unit mass. Both work and heat crosses the boundary. If you have closed system, if you have open system, they are not related exactly directly to the state. Yes, they change the state, but they are not associated with the state. For example, W1, 2 happen between 1 and 2. So the flow pushes a turbine, pushes a blade to rotate. It means it's not exactly 1 or not 2. It's something happen between 1 and 2. I took some energy or I gave some energy. I took some heat or I gave some heat. So it crosses the boundary. They are crossing the boundary. Can you follow up with me, guys? 5.2, page 5.2. The third point is state or system have energy. Yes, the system has energy, like internal energy, enthalpy, flow work, but it's not heat or work. You will never ever see W1 or W2 or W3 or Q1 or Q2. There is nothing called that. It's impossible. Heat and work, next one, associated with process, not a state. State, P, V, T, X, H, U, these properties of single state, equilibrium state. Path function. So the work or heat, they are path function. Let's take an example. If you remember from, like for example, mechanical compression or tension, the stress strain curve, if you have a strain stress curve, you remember this? Something like this for ductile material, correct? If I told you, we're gonna compress until, let's say, this point. So this area is the energy stored in the system. Do you remember this, guys? This was force distance curve. Was force distance curve. We divide by area, became stress. We divide by initial length, it became strain. So the stress strain curve. This area, guys, is the energy because it's F delta A. It's work. It's how much energy. So if you are like this, if you go from this point to this point, you get this area. But if you go from here to here, another area. So this path, you know how much energy. If you have another path, if you have another material, this is aluminum. Let's say you are talking about copper, which is little bit larger, you get bigger area. So you have different areas. It's path dependent. This area under the stress strain curve, which is energy stored in the system. Make sense? So this work, or even heat, it's path dependent. Let's take an example. If I told you, if I said to you that you have a process, two processes. This is two processes here. PV, PV. Maybe big V or small v. These are two processes here. Can you see them, guys, here? Can you see the curves?
Yeah, we can see it.
So let's say this set one here. Exactly same set one here. Exactly the same. And also state two here. Exactly same as state two here. So this pressure and this volume, let's 1 exactly here. P1, V1, V2, P2, P2, V2. This is a point, correct? This is exactly the same point here, the same here. Exactly the same point here, the same as here. Clear? I went from here to here. Let's say when I do compression, it was like this. This is a compression. In the other one, I did also compression, but the fluid somehow behave differently. Let's say like this. Which one is better? And why? 1, 2 in the left or 1, 2 in the right. They are the same states. One, the same as state 1. State 2, the same as state 2. The same, everything is the same. Which one is better? This one is better. Why? Because this area is smaller. But this area is much, much, much larger. I need too much energy to reach the same action. So which one is better? To pay more or to pay less? Which one is better, guys? So this area is the work. W1, 2. This is the work. However, you went from 1 to 2. The same 1 to 2 here, but the work here is different from here. Ah, that's a very good example because you see now, state 1 has some properties. State 2 has the same properties. Different properties, I mean, but P2 will be, and V2, actually, this is V2. So you have the same states here and here. And property here, pressure, volume, temperature, specific volume, entropy, anything you have here. The same thing between this and this and this and this. However, the work here is different from here. Ah, that's good because you see here 1, 2. So I paid here less than here to go from 1 to 2. I pay here much, much less to go from here. Pay here a lot. Pay here less, much, much less. I wish I pay 0 between 1 and 2. I wish everyone wished to pay less. Okay, so exactly the area under the curve is the work. Let's drive it. Let's drive that the area under the curve. So before that, we used to use for W, delta W and delta Q. These are the changes or the incremental in heat and work. They are not D, like DT with temperature, with pressure. Because this is called exact differentiation. It's called exact differentiation. This is called local differentiation, like partial. There is a big difference between this and this. This is path dependent. This is path independent. I don't care about how the way I go, but this is I care much about how I go, or even heat. So W, for example, 1, 2 is equal integration from 1 to 2 along this path. Delta W. The same for Q1, 2. It's integration from 1 to 2. Delta Q. Maybe you need just, you don't need it closed. You need to, it's just integration like this. But this is not delta. This is not D, sorry. This is partial. This is delta small. Okay, guys? Okay, guys?
Yep.
Okay, let's take an example of these two before we move ahead. I'm gonna give you a quick review or recall for the difference between exact differentiation and inexact. This is called exact, this is called inexact or local. Inexact. Okay, it's still lecture 5. So let's move to the other side. So if I told you delta T, integration of delta T from T1 to T2, you can say here simply it's because I'm integration 1. What integration of 1, guys? Here, integration of 1, delta T is what? Is what?
T.
T, perfect. From T1, integration of 1 delta X, it's the X, 1 delta Y, it's Y. So upper minus lower, upper limit minus lower limit is just delta T. Perfect. But you cannot say that with delta W. You cannot say it's W2 minus W1. Can I say that? You know why I cannot say that, guys? It's so simple, because there is no property called W. You will never ever in your life see property called W. Have you ever seen a property called work? My work property is this? No, it will never ever hear this or any ever. So that's why I call this inexact. It's called inexact derivative or differentiation. This is exact. Yes, this is always correct mathematically. Yes, integration of 1 is T or X delta X. This is D. Yes, any D integration is fine. But delta, nope, nope, because it's not associated with state. It's not associated with as a property. This is a property. Yes, this is fine. T2 minus T1. Yeah, that did change. Because I don't care from where I go to here. I just care about this and this, the delta T. But here, no, I care about delta T. Okay? Make sense, guys?
Yes.
There are two forms. I want to make sure that this is understood very well. This is associated with process. This is property. This process, property. I cannot say W2 minus W1, but I can say T2 minus T1, P2 minus P1. So what we wish now, we wish we can write this guy in terms of other properties, P, V, T, U, H, and so on. The same for Q. We wish to write this in these properties, P, V, T, U, H, S, X, so on. We wish to write in terms of other properties, to be able to integrate, be able to find out what's going on. There are two known forms of energies or work, two identical works. One is heat, or we can say work or heat, it doesn't matter. So let's think about these two. We can say heat and work, they are very, very same, but not exactly the same. They are both energies, both joules or joule per unit mass, it's okay. And they are the same treatment of everything, but they're quite different in terms of physics. One is usually adding, like for example, heat, it has two purposes. It increases temperature or change phase or change, like for example, if I have water at 10 Celsius, I can make it 100 by heating up. If it's ice, I can make it liquid by changing its phase. So heat can either increasing temperature, change phase, or both. It can does both. Okay, but work, I take usually mechanical action. I usually take mechanical energy. For example, I drive the turbine. I run the fan. So let's think about the two forms of energy very known. It's called, the first one is electrical energy and moving boundary. Like for example, piston cylinder or any. So there are two known for electrical energy and moving boundary. What is electrical energy is W dot equal this power VI. You know guys the boiler? Can you see guys this? Is the screen is good or not? Can you see this guys? Where is the yes man? Okay, what's your name? Hello, what's your name, sir? Okay. Somebody say yes.
Yes.
Okay, yes. What's your name? What's your name?
Emmanuel.
Okay, Emmanuel, you will be the yes and no man, okay?
Whoa, whoa. Relax.
You have now a position, okay? So yes and man now, he said, this is clear. No, we don't want to hear your joke. You're laughing. We need to hear yes or no, okay? I'm not kidding, by the way. Okay, this is a power. If you know, guys, the coil, you know, like when I heat up this water today, I use boiler. In the past, in old days, there is some kind of coil like this. I don't know. Have you ever seen it or not? Like something like this.
Yeah.
So you put it in the water, it warm up the water. So maybe some of you, this is like have a cable and you can plug it in the electricity. Anyway, this coil, when the electricity move through, it heat up. That's exactly the boiler, correct? So what happened here? If we multiply the volt, if it's constant, it was before that. It was different. It was before that. Yeah, it's a VI. If the volt is constant and I is constant, this is a work. This is a power. Actually, this is W dot or Q dot. If you want to make it exactly heat, you can write Q dot, the heat, which is exactly energy. The volt times the current gives you how much? What? How much power? So if you multiply here by delta T, both sides, delta T, and delta T is time here. T small is time. T capital is temperature. And you integrate, here is Q capital. Here is, if V and I are constants, so we can say just V, I, delta T. Delta T can be like this, delta T. It means that the period of time, how long you run this. So let's say I give you the water for this volt, for this current, for like 10 minutes. Multiply, of course, subdue by second. Multiply volt in volt, ampere in volt, and current in ampere, and time in seconds, you get exactly joule. This is joule. This is joule per second or what? So remember, this is joule per second. So you can get exactly how much heat from this from this coil or this boiler. Okay? Okay, guys? Make sense?
Yes.
In the exam, yeah, hello, yes, man. So this is gonna be given in one of the problems. I'll give you a boiler, I'll give you a coil, it heat up, it adds some energy to the system. So you can tell me how much energy, multiplied by volt, by current, by time. Volt, let me write it down. Volt, current in ampere, and time. You have seen this a lot of time, I'm sure, in even high school. How about moving boundary? Moving boundary actually was
like this. We said the work, for example, let's say the other side, the work is FD, correct? Force times distance. Let's talk about locally. It's, keep going. It's PAD. So the force is pressure times area. Yeah, force is pressure times area. Then because pressure is force per unit area. So I can replace force to be PA, pressure times area. We defined before. So A times D is defining the volume. So it's PV. The work is PV, the pressure times volume. This is the total work. How about if I talk about local? So if I said delta W, it's equal P delta V. Guys, here I wrote something so important. When I go to W, I wrote delta small. I wrote delta small. But when I go to the V, I wrote D because it's exact differentiation. So the difference here, this is inexact differentiation or derivative. This is exact derivative. So this is how the work can be written in terms of a property. It's always delta W equal PDV. Delta W is equal PDV. Delta W is PDV. Or W itself is integration of P delta V. Now I can integrate, no problem. That's integration. Yeah, we are happy now. We are seeing mathematical, very typical identical equation. Guys, can somebody tell me what this W12 means? PDV. What does PDV mean? You know what is this? Can somebody tell me what does PDV mean? Huh? It's area under the curve. So if you are able to plot the PV diagram, if you be able to draw the PV diagram, let's say this is a process 1 to 2, the work exactly this area is the area under the curve, exactly like the stress strain curve. Its area under the curve is the energy stored. So between 1 and 2, this is 1 and this is 2, the area under the curve is work. This P dV, area under the curve, P dV. Clear, guys? Is it clear? Yes, man.
Yes, sir.
Yes.
Thank you, dear. Okay, so let's go back to take 4 special cases. So if we have the pressure function of volume or volume function of pressure, we'll be able to find the work done in between 2 states. So let's take 4 famous, very known special cases. Very, very known special cases. They are 1, 2, 3, 4. 1, 2, 3, 4. If the volume is constant, like for example, rigid tank. Some process, the volume was constant. If the temperature is constant, do you remember, guys, what we call this process? What we call temperature is constant?
Isothermal.
Isothermal. How about this one? Isochoric or isometric. How about this one? Isobaric. How about here? This is called polytropic. I'm sure you have heard about all of these. We're just recalling what is going on and apply PDV. That's very good. The first one, we have PDV. PDV, this is the work done. Oops. PDV. So the PDV here, guys, is simply is 0. Why? Why, guys? Why PDV is 0, guys?
Because volume doesn't change.
Exactly. Exactly. Work means you change the volume, PDV. So delta V is 0. No volume change. V1 equal V2. Pressure change it or not, I don't care. V equal V. It means there is no work. Rigid, I can add heat or take heat. That's it. A rigid tank, rigid container. Correct? Like for example, the boiler at home. This is exactly, there is no work. Just I'm adding heat, removing heat. Temperature is constant. Now we are talking about, for example, ideal gas. Because it's hard to manipulate the steam table or even compressibility correction equation, but we can use, so these special cases mainly for gas. However, the first one can work for anything. This is anything, gas, liquid. But this is mainly gases. Like for example, we said PV equal MRT. We have here something very important. We can say PV, like PV, this is work, or PV is sole work. But this work as a work, and this work per unit mass. This is W capital, this is W small. We gave here a little bit wing like this. So this is a PV small, or PV specific volume, it's still work, but per unit mass. So this work and this work, but this work per unit mass when I have a specific volume. So you can write this way: PV equal, or PV equal RT. Both are correct. So W small is integration PDV. So divide by mass, divide by mass. If I have capital, I have here capital. If I have a small, I have here small. So PDV, what is PDV, guys? The temperature is constant. If this is constant, this means P is inverted proportional with V. So it means, let's say this is C. So P equals C over V. I can't remove this. Say it's C over V, dV, correct? Equal C ln V from V1 to V2, which is C ln V2 over V1. This is the work done through isothermal ideal gas process. Again, so R constant, T constant in this special case. So RT is constant. I call it, for example, C. See, C is RT. R gas constant, T absolute temperature. So PV equal RT. So P equals C over V, RT over V. It means I can replace this guy by C over V, RT over V. RT is constant, take it out. RT outside, it's ln V, 1 over V. Integration of delta X over X is ln. So you need to remember, integration of delta X over X, ln X. Integration X to the N delta X is X to the N plus 1 over N plus 1 plus constant, but N not equal minus 1. If N minus 1, it's ln X. So delta X over X, ln X. X to the N delta X is X to the N plus 1 divided by N plus 1. But N not equal to minus 1, which is this special case. This is the integration. So we can replace P in terms of V. Integrate this, it's ln V. Upper limit minus lower limit is division. So V2 minus V1. So ln A minus ln B, it's ln A over B. That's definition of algorithms. Ln minus ln is ln A over ln plus is ln times. Like ln A plus ln B, it's ln A times B inside. I think you know that all of this definition. So it's just simply RT. So if I give you a system, it's isothermal. Temperature is constant. And you have V1 and V2. And of course, you have T1, which is T2. And you have gas constant. This is gas, ideal gas law. You can get the work done between 1, 2. How about pressure constant? This is easier. P V equal RT. Or actually, we don't need this even. We don't need this. It's just W. It's just PdV. That's even general. You can use this without leaving gas. So pressure is constant. Take it out. P just delta V. Integration of delta V is what, guys? Is delta V. Is V2 minus V1 or delta V. V1. If this is W capital, so if you want this W small, this is V small, this is V small, this is V small, the specific volume. And this is work per unit mass. Do not ever say specific work. Do not ever say that. Okay, if I said that, you're wrong, doctor. This is wrong. You need to say work per unit mass. It's PdV, V2 minus V1. Polytropic, it's very good relation. It says P equal C V to the N. P, or actually PV to the N, it was rho. PV to the N equals C. Say constant. It's the pressure proportional to the volume to the power N. And N is polytropic parameter. It's a very known, I don't know, do you remember this or not, but this is a very known equation for fluids, for gases. Some gases behave polytropic, constant entropy, so this is called polytropic. It's called what? Polytropic. So N, usually the specific heat ratios, K. So let's say PV to the N, math. Think about math now. Pressure, so constant over V to the N. For example, we have process from 1 to 2. 1 was P1, V1, 2 was P2, V2. Of course, we have T2, we have T2. Correct? So you can say P1, V1 equal this, or P2 equal P2, V2 to the N. And N is given, number is given. It's called polytropic parameter or coefficient. Okay, guys? So P1 V to the N equal P2 V to the N. It's a constant process. Something happened. This is always constant. Between state 1, state 2, state 3, if it's still continuously polytropic. Okay? For example, if I told you here N equal 1, guys, if N equal 1, do you know what is this? If N equal 1, for example, if this N equal 1, for example, PV to the 1 equal constant. Have you seen this before? P equal 1, N equal 1. What is this, guys? What is this? What is this? It's isothermal. If N equals 0, what is this? It means PV to the 0, it's 1. So P equal constant. What is this? It is this guy, pressure constant. So N equals 0, it's pressure constant. N equal 1, temperature constant. Like similar to this guy is constant, it means PV equal constant. But PV to the N, something else. Substitute back in the work. So the work equation like this. W PdV, which is P, actually P is equal to C V to the N delta V, which is C over 1 minus N times V 1 minus N minus V 1 minus N. This is the work. And C is P1 V1 to the N, for example. C is P1, this C, I call it P1 VN, V1 to the N. This is C, the constant. This is C, I put it here. Here, it's constant during this process. So I took V to the end up, add to the power 1, divide by new power, upper limit minus lower limit, give you this. Okay, guys, in the exam, if you go to bridge 5.3, please, you will find all this given in details in the bottom of 5.3. Okay, let's move now to the last, the section 4.2, which is about first law of thermodynamics. So first law of thermodynamics, guys, you are following me? In the exam, for example, next lecture, we have a quiz. I'll ask you, give me the work. It can be rigid tank, it can be constant pressure, it can be constant temperature, it can be bolotropic. I'll give you everything you need to give me how much work, or I give you the work and you give me the N, and so on. So some inputs and some outputs. Now, the first law of thermodynamics 4.2. This is a very important section now. First law of thermodynamics for closed system. First law of thermodynamics, guys, energy neither can be created or nor destroyed, but it can transform from one form to another. We have two typical case here for closed system. Rigid tank, we have piston cylinder. This is a very typical rigid tank, like this tank. I can add heat, remove heat. Here, I have piston cylinder. I can add heat or add work. So I have work or heat. And this is the boundary. This is the system. This is a piston. So this is two identical case for closed system. These two famous examples. We have sign convention, guys, here. A very typical sign convention. Usually heat added to the system. We use positive. Usually work given by the system. We call work done. Work A done. It's positive. That's it. For example, if I move forward, it's positive. If I move backward, it's negative. Okay, this is my sign. I said I'm moving forward, positive. Backward, negative. We gave a conventional sign. We said, if heat, guys, are you following me?
Yeah.
So the rigid tank, if we add heat, it's always positive. If I took heat, I will consider it as negative. This is our convention or the sign that we're gonna use in the rest of the course. Whenever you said heat addition, it means positive. Heat rejection, cooling, it's negative. So this is the positive. If I took it out, it's negative. So when I add, I said 30 megawatt. This is heat addition, positive. It's as a color. So this is heat addition by, for example, 30 megawatt. For example, I add power. This power added to the system. If I multiply by time, it became energy. The work done by the system. Give it to me. I have a turbine. It give me power. It give me work. This work. So give me 30 megawatt. It means done by the system. If I compressed like pump, I gave power. Compressor, I gave power. It's negative. So this is our conventional sign. So the first law of thermodynamics is so simple. It's so simple. The most simplest thing ever. Everything in our life is conservative, except politics. So E in minus E out equal delta E system. So if something is not going in or something going out, the delta system is what? The same, zero. If there is no heat addition, no work in, no work out, no heat out, this is delta system equal to zero. It means energy 1 equal energy 2. Okay? So this is called conservation of energy. Conservation is very, very meaningful word. You have $100. You bought a book with $20. it means you have $80, correct, in your pocket. Have you ever imagined that you put your hand in your pocket, you found $200, 90, 70? No, you have 80. The remainder between this minus this. If you put something else, 80 minus 10, it became 70. Yeah, we have 70. If you have 70, if you take some $5 from anything, it's 75. This is called conservation. Something is not gonna neither created or destroyed. You have energy, you will have it forever. If you took some, if you add some, the remainder is what you have. 10, 100 minus 20. So if I feel guilty when I say that, 100 minus 20 to the, I don't know, engineers. 100 minus 20 equal what? My son can do that, by the way. 80 minus 10. So this is the conception of conservation. Everything in our life is conservative, except President Trump. Anyway, so here we have 100 minus 20 is 80. 80 minus 10, it means we have to have the energy the same. So if I add some energy to the system, to add it to this, took some energy, removed from this. So if we put this here, we find a very, very identical formula for this system. It's called for open closed system. This is closed system. Closed system means control mass. It's E, it's W, or Q minus W equal delta E, or E2 minus E1. Because we used to say Q is positive when I add it to the system, and W need to be done, so it's positive when I took it out. This is in the system, this out of the system. We said here, energy in, like heat, energy out, like work. That's why I said Q minus W. If we use another conventional notation, we're gonna say, for example, Q minus W, but Q add, W add. But we said here, always Q heat addition, W work done equal the change in energy in the system. Always work done, always work done, always work done by a system. That's always the positive sign. If it's given to the system, it's negative. So negative times negative, it's positive. Energy of system increases. This heat addition to a system, not by a system, to addition, it's positive. So if I had heat, it's heat. The system of the energy increases. If I took it from the system, energy of the system decreases. Q minus W equals delta E. This is, do you have any question, guys? E can be delta U, can be kinetic energy, can be potential energy. This is a three known equations. Usually we talk about the first one. We usually talk about internal energy. So this equation, if we don't have kinetic energy, potential energy, so Q minus W equal delta U, or Q minus W equal delta U. Heat addition to the system. Heat addition to the system, Q capital, like this. W, work done by a system. U, internal system of a system. This is energy, total internal energy. U2 minus U1. This means U2 minus U1.
I don't know what's going on.
What? Q small is heat addition per unit mass. Work done per unit mass. This is specific internal energy. Okay? So let's see you next lecture. Do you have any question, guys? We are done now. Do you have any questions? If you have any question, please. I'm gonna solve some problems in the beginning of the next lecture. Do you have any question now? It's almost 11:50. 1 minute. Do you have any question, guys? Feel free to
Are
ask.
those books still available?
Yes, I have still like 7 books. If you want,
Is it?
if you
I
want to go to
emailed
the
you about
school,
it.
if you can send me your address, I'll give it to you. No problem. I'll come stop by and drop it for you. No problem with me. Send me an email.
Okay.
The very 7 emails. I'll give them books.
Okay.
No, not like that. So if you need them, let me know. Pick up one of them, the title, give me your address. I will stop by and drop it for you. No problem with me. If you want to come to school, it's okay
Sweet.
with me also. Okay, guys?
Sweet. Thank you.
Please work very hard, guys. Very hard. We have midterm. I'm nice. I'm make joke, but when come exam, I'm very bad. Very bad. Seriously. So consider that as alarm for you that I'll never ever give you 1 point more than you deserve. Okay, 1 point. Remember that. The last year, the same happened last year or the evening year before. I always tell the student, you will get only what you did in the exam, in the midterm, or homeworks, on anything. So do your best to understand everything yourself. Do it yourself. Make your mistakes yourself. Use the table. Use a chart. Make sure you will be able to get the value yourself. You have a TA to help you. I think he can hear us now. You have me to help you. You have friends to help you. Ask me anytime. Send me an email and I will reply within hopefully 24 hours. I'll reply with any technical question. Okay? Any technical, like how to use this, how to do that. I will even draw it for you. You have office hours. You have email forever. You can ask me any question anytime. Okay? Do you have any questions?